In this video, we'll cover the problem all paths from source to target. In this problem, we're given a directed acyclic graph, a DAG, that looks something like this. And we want to find all of the paths from some source node to some target node. Now, we are told that the source node is always 0, and the target node is always n minus 1, where n is just the number of nodes in our graph. For example, in this case, we're going from 0 to 3. So we can go 0, 2, 3. That's this path right here. We can also go 0, 1, 3, which is this path right here. This example is a little bit more involved. Feel free to pause, take a look at the paths here, and kind of try to mentally construct what the answer should be to get from node 0 to 4. You can see a simple path is 0, 4. That's what we see here. 0, 3, 4 is another path, and there are more that you can look through. Now, the key for this problem is really understanding recursion, because if you have a solid understanding of recursion, we can implement this problem in a way that is pretty straightforward. One thing I want to mention is that the graph here is actually stored really nicely. We have an array, but it's basically an adjacency list. At index 0, we have all of the nodes we can get to from index 0. Index 1, we have all the nodes we can get to from index 1, and so on. So it's basically structured like an adjacency list. Okay, conceptually, the way we're going to solve this problem is we are going to have a recursive function. Remember, the key with recursive functions is you want to assume that they magically do exactly what you want them to do. So let me I could explain it in this example, but it's going to be a little too simple to properly demonstrate the example. I'm wondering if we have a better option. Okay, we're going to do something a little bit weird. We're going to focus on this example, but we're going to pretend the source node is 1 and the target node is 4. So let me just quickly try to model out what's going on. So imagine that source equals 1 and the dest, or I'll call it the target, is 4. There are two paths that I'm seeing that are kind of obvious. Path number 1 is go from 1 to 3 to 4. Path number 2 is go from 1 to 2 to 3 to 4. So the first path, which is the one at index 0, is 1 to 3 to 4. The path at index 1 is 1 to 2 to 3 to 4. Now, what we're going to do is we're going to write a function that takes in a current node and the target and returns all of the paths from the current node to the target. So let me write that. We'll use some pseudocode. We'll say f, just some generic function. We'll name it later. But it takes in a current node and a target node, and it returns an array of all of the paths from the current node to the target node. For example, if we called f of 3, 4, that gives us all the paths from 3 to 4. Well, there's only one. There is this path right here. But note, it's an array of arrays because it's an array of paths, and each path is its own array. If we called f of 2, 4, well, again, we only have one answer, but now it's going to be 2, 3, 4. Because we can go from 2 to 3 to 4. And I believe that's the only option we have. Yes. So the key is we want to figure out f of 1, 4. That returns what? What we're going to do is we're going to say find every node we can get to from 1. So that's going to be 3 and it's going to be 2. Make a recursive call with those as our current node and get those answers. So we have these answers and these answers. And then for every single one of these paths, just stick a 1 at the beginning. Because we know we can get from 1 to 3. Which means if we have 3, 4 as a path, then a valid path here is going to be this exact same path. I can actually literally copy and paste it. But we have to stick a 1 at the beginning because we're not currently at 3, we're at 1. Oops, this should be a 2D array. But also this path works. We could literally take this path. However, we have to stick a 1 at the beginning because we're not at the 2 node, we're at the 1 node. But we know that we can get directly to the 2 node from the 1 node. So what we're going to do is we're going to say go through each of my neighbors, make a recursive call to get all of the paths from the neighbor to the target, and then add myself at the beginning of each of these paths. Let's go ahead and try to see what this will look like in code. So to get us started, I'm going to have another function. So we'll say get paths from node to target. And it'll take in the graph, and it's going to take in this current node and the target node. This function is f, to be clear, this right here. So I'm going to declare a constant for our start node, just because it is kind of random that it's 0, and I want it to be clear. So this graph is going to take us from the start node, and then the target node is just always graph.length minus 1, the very last node in the graph. So we can throw in the target node here as well. But remember, this function is kind of generic and recursive, so that it's not only working for the start node and the target node, it just works for any current node and a target node. And here is where we're going to use our depth first search. This is also where we're using our recursion. So remember our template, we have our base cases, we have our process node, we have our recurse on neighbors. Base case we'll come back to. Process node is not too involved for this problem. We want all paths from node to target. So I'm just going to create an array for this. And we're going to make sure in the very end that we return this array. Now, recursing on neighbors is where this is going to get interesting. Remember, we should assume that our recursive calls work magically. So when we look at, imagine we're at the 1 node, and we're trying to get to the 4 node. When we call our recursive call, and we pass in 3 and then 4, we should assume that gives us our desired output, which is this. And when we make our recursive call with 2 as the current node and 4 as the target node, we should assume it magically gives us this output. And we don't know how, we don't care how, we don't need to think about how, it just does. So what we'll do is we'll say, first of all, get our neighbors. So it's going to be graph at current node. We'll say for each of our neighbors, so remember, these are just going to be numbers like 3 or 2. We're going to make our recursive call. So we're going to say get path from node to target. Pass in the graph, we'll pass in the neighbor, and we'll pass in the target node. Here we'll say paths from neighbor to target here. That is going to be these guys. Well, actually, it's the 2D array, so it's these guys. Then we can iterate over each of those paths. So that'll give us the 3-4 path and the 2-3-4 path. So we'll say for each path of the paths from this neighbor to the target, what do we want to do? Well, we know that if we take that path, this path, which is going to be something like 3, 4, and then we put our current node at the beginning, then we know that we have formed a path from the current node to the target. Because remember, we assume our recursive call works, this is magically returning paths from the neighbor to the target. And I know I can get from my current node to the neighbor, therefore I can get from the current node to the neighbor and then the neighbor to the target, and that is a full path. So we can say path from cur to target is going to be, I'm going to create an array, I'm going to insert my current node, and then I'm going to spread the rest of the current path. So we take this right here, this is giving us 3, 4 right here. But before the 3, 4, we're inserting our cells, which is a 1. So this is going to look like 1, 3, 4 when we focus on this path right here as our path variable. Okay. Then once we have something like this, we know we have found a path from the current node to the target, so we can add it to this array here. So we'll say all paths from node to target dot push this right here. And because we are copying right here, when we do the spread, it automatically copies. Then we don't have to worry about any issues with references. We're just copying every time. So there's no possibility that this path here gets changed or something like that. It is very space inefficient to be copying so often. However, we kind of have to be space inefficient for this problem because we have to be looking at lots of different paths where each path can be quite long relative to the length of the graph. Okay, conceptually this logic makes sense. That should allow us, if we assume our recursive call works magically, then it should allow us to get all of the paths from the current node to the target. The one thing we want to check is make sure we're terminating this recursion properly. So when we're at the 3 node here, we're going to make a recursive call to our 4 node. So we're going to pass in graph 4, 4. So that is the base case, right? When the current node is the target node, we're done. So we can say if current node is equal to target node, we're done. Now what do we want to return in that case? Remember, we have to stick with the same thing as before. it must return an array of all of the paths from the current node to the target node. In this case, it's an array of all of the paths from 4 to 4. Well, there's one path from 4 to 4, and it just consists of the 4 node. So this is the path, and we want an array of all of such paths. So we need to return this 2D array here. So we'll return that guy, except we want current node here. Note that we have an array of arrays, which is a little bit confusing, but notice we have the same thing here. Here, this is an array, and what we're pushing into it are entire other arrays. So if this guy's returning an array of arrays, then obviously our base case needs to also return an array of arrays to be consistent with the rest of the problem. So when we're at the 3 node, we'll make a recursive call to the 4 node. We'll get an array of an array containing 4. We're going to insert the 3 at the beginning and then spread the rest of that array. So this is going to be an array that's like 3, 4. And we're going to push that and say, hey, this is a path from 3 to 4, which it absolutely is. And that's going to bubble up, and we're going to go to the 1, and we're going to say, all right, we have 3, 4. Now put 1 at the beginning and get 1, 3, 4, and that's one valid path. Same thing happens going to the 2 and going up to the 1. Okay, let's go ahead and run this code to see if it works. Looks like it works in this case, and if we submit it, yes, looks like it passes the tests there as well. All right, well, that's all for this video, and thank you for watching.